This is the Discovery Files podcast from the U.S. National Science Foundation. From a historical existence as a fundamental theory in quantum physics to broad implications for the way information is handled in the advancing modern field of quantum computing, quantum information science is revolutionizing the world around us, with applications across the sciences and beyond, and examples appearing in popular culture. A future powered by uniquely quantum-based technologies is on the horizon. We are joined by Scott Aaronson, the Schlumberger Chair of Computer Science at the University of Texas at Austin and director of its Quantum Information Center, who has spent several decades working with quantum theories and raising awareness of the capabilities and limitations of quantum computing. His work was recognized in 2012 with the Alan T. Waterman Award, the nation's highest honor for early career scientists and engineers. He is currently on leave to work at OpenAI, where he has been focused on the theoretical foundations of AI safety. Professor Aaronson, thank you for joining us today.
Thanks for having me.
So I'd like to start with a little bit of background, and I'm wondering what about quantum mechanics first captured your imagination?
As a kid, I read popular science books. I read things that didn't make sense to me. Like they said, well, the electron is not really in one place as it orbits the nucleus, right? It's in a sort of smear of probability wave all over the place. And then I said, well, isn't that obviously just a fancy way of saying that you don't know where it is, right? Or, I read that somehow what Richard Feynman did that was so important had to do with summing up over all the ways that a system could possibly get from one state to another state. Somehow they all occur simultaneously. Or I heard about spooky action at a distance. If I have two entangled particles, then somehow I measure one of them and the other one immediately collapses. And then you say, well, but wait a minute, isn't that faster than light communication? Isn't that supposed to be disallowed? And they say, well, no, it's not really faster than light communication. And then you say, well, then what is it? If it's just a matter of I look at one of the particles and then I learn something about the other particle, that could also happen classically. That wouldn't be a big deal, right? So what are we even talking about here? And again, the message that you would get was like, don't even try to understand this. Anyone who thinks they understand it, doesn't understand it and blah, blah, blah. And I think the fact that that is what filters out, provides this enormous opening for, the hucksters and the woo merchants and so forth to put, their preferred spin on it. I think that quantum information is just immensely clarifying. You can't explain it without just sort of immediately telling people, what is the core point about quantum mechanics, right? And it's not about, nature being probabilistic, right? It's about a new way to calculate the probability that something's going to happen. This is kind of the key twist, that instead of probabilities, we have to use these other kinds of numbers that can be positive or negative or even complex numbers. When I started reading about quantum computing shortly after Shor's algorithm was discovered, in 1994. So popular articles came out about it. And they basically said, well, the way that this miraculous new factoring algorithm works is that it just tries all the possible divisors in parallel, right? And then sort of nature magically picks the best one. And again, there were these things that didn't make sense about that to me. Like, doesn't that sound too good to be true, right? And also, if it's that simple, why did you need the brilliant Peter Shor to think of it, right? Sounds like I could have thought of that. But then, I wanted to read about it to understand what was going on. And the web itself was fairly new at that time, but there were already websites, explaining the basics of Shor's algorithm, papers, lecture notes. So I started reading, and it was like a revelation to me to find out that quantum mechanics is actually much, much simpler than, I'd been led to believe once you take the physics out of it.
You just have to get it clear in your mind and that it starts making sense.
Right. And the way people thought about it in this emerging field of quantum information was really just as a certain generalization of the rules of probability. So you have to deal with these new numbers, these amplitudes, which are complex numbers. But then basically, your state, the state that your system is in, is a list of amplitudes. It is a vector of amplitudes. And now there's just a set of rules for how we operate on these vectors. And I could understand this, right? It was just matrices and vectors and complex numbers. And so it was slightly unfamiliar rules of computation, but, they're just rules of computation that you can learn just like you learn the classical rules. And then, within a few years, I was, able to start working in the field. So I did some summer internships at Bell Labs that had nothing to do with quantum computing, but my boss was nice enough to let me spend time reading up on it. And then I discovered that Love Grover, who was the discoverer of Grover's algorithm, the second most famous quantum algorithm after Shor's, and this had been just a few years prior, that he actually worked in the same building as me. And so I went to talk to him, and then he was nice enough to offer me an internship the following summer. And that's where I met Ashwin Nayak, who was a student at Berkeley studying with Umesh Vazirani. And that was really the center of quantum computing theory in the world. So, I formed an ambition that I wanted to go there for grad school. And I was lucky enough to be admitted there. Although it was not admitted to do quantum computing, I was admitted to do AI, which I was also very interested in at that time. And I spent a year doing AI and machine learning until, I decided, well, this will probably be very important for the world, probably even important on a shorter time scale than quantum computing will be. But quantum computing was just so mathematically sweet. And, there were just so many non-trivial things to prove and to understand. Whereas with AI, it seemed like everything boils down to just doing some empirical evaluation and then staring at some bar charts. And, I was just not as skilled at that as other people were. It's funny that a quarter century later, I very much feel the same tension. I am now dipping my feet into AI again. It is, of course, much, much more important even than it was then. And yet it is so hard to say much that is useful about it as a theorist. So in AI, the experiment has been so far ahead of theory. And in quantum computing, it's the reverse, right? Experiment is just starting to catch up, like right now, to where theory was, let's say, 30 years ago.
Now, I'm going to skip ahead about 15 years of your work here and ask you about some of the things you learned over the course of your career. And on your blog, you mentioned, is a quantum computer merely a souped up classical computer? So I think this is something, as people are seeing quantum computer in pop culture pop up or on the front of magazines and things, kind of differentiating what they actually are seems important to me.
So on the one hand, you'll get people who say, well, a quantum computer is faster than a classical one. Okay, how many times faster? Is it 1,000 times, 1,000,000 times? This misses the point that it's harnessing nature to do computation in a totally different way. So what we really care about is the scaling behavior. At what rate does the number of steps increase as I'm trying to solve a larger and larger problem, right? If that scaling is, let's say, linear or quadratic, like with the size of the problems, like n or n squared, then I say that that's usually pretty good. But if the scaling is exponential, like 2 to the n power, that quickly gets into astronomical territory. Or, if n is 1,000, then, 2 to the 1,000 power is much more than the number of atoms in the whole observable universe. So the point of a quantum computer is to change the scaling behavior of certain specific problems, even we think from exponential to polynomial. But now you get the people who know that much, but they say, well, then what you must be saying is that a quantum computer does this by just trying all of the possible answers at once. So if I had, let's say, a solution that was a string of 1,000 bits, so that now there's 2 to the 1,000 possible solutions. With a classical computer, I would have to just try them all one by one, maybe, if I didn't know anything more clever to do. Whereas with a quantum computer, the idea goes, I would just somehow try them all in different parallel universes or all in superposition and then instantly pick the best one. Now, that sounds too good to be true. And unfortunately, it is too good to be true. That's not how it works. Okay, but I could explain exactly what the issue is. With a quantum computer, you can actually create what we call a superposition over all of the possible answers, even if there are 2 to the 1,000 of them. Okay, that is even an easy thing to do with a quantum computer. The trouble is that for a computer to be useful, at some point you have to look at it. You have to measure. You have to get an output out. And in quantum mechanics, measurement is this very, very destructive operation. So if I just took an equal superposition of all the answers and measured to ask for an answer, not having done anything else, then the rules of quantum mechanics are unequivocal that all I'm going to see is a uniformly random answer. And now, of course, if I had just wanted a completely random answer, well, I didn't need a quantum computer for that. I could have just flipped a coin a bunch of times or just used the random number generator in my classical computer. So the only hope of getting an advantage from a quantum computer is to take advantage of the way that these amplitudes, which are the basic numbers of quantum mechanics, being complex numbers, work differently from the probabilities that we're used to. Normally, you would talk about, a 30% or a 50% chance of rain. You'd never talk about a negative 30% chance, right? That would be nonsense, much less would you talk about a complex number chance, okay? And you don't do that in quantum mechanics either, but in quantum mechanics, before we get the probabilities, there are these other numbers, these amplitudes, which can be complex numbers. And now the way it works is this. For each possible outcome of an experiment, so for example, every place that a particle could land on a screen, or every possible answer that I could get by measuring my quantum computer's state, in order to know how likely it is that I'll see that outcome, I have to first find an amplitude for that outcome, okay? And finding the amplitude means adding up an amplitude for every possible way that this event could have happened. And now with every algorithm for a quantum computer, the central idea is to choreograph a pattern of interference, which has the property that for each wrong answer, each answer that I don't want to see, some paths leading to that answer have positive amplitude, others have negative amplitude, so they cancel each other out, right? Whereas for the right answer, the answer I do want, I want all the contributions to its amplitude to be in phase, pointing, more or less the same direction, constructively interfering. If I can arrange that, then when I look, that Born rule tells me that I will see the right answer with a large probability. Okay, the tricky part is I have to do that even though I don't know in advance which answer is the right one. If I knew, what would be the point? And also, I have to do this faster than anyone can figure out how to do the same thing with a conventional computer. Again, otherwise, what would be the point? And so it's really mostly for very, very special problems that people know how to get a big advantage from this trick, right? When Feynman introduced the idea of a quantum computer more than 40 years ago, at that time, he really only had one application in mind, which was simulating quantum mechanics itself, okay? And I think decades later, the truth is that's still the most important application economically that we know of. And it wasn't obvious that this weird trick of choreographing interference would ever be useful for speeding up the solution to any problem that was not itself about quantum mechanics. That it can help for classical problems was a great discovery in the 1990s. Basically evidence for this accumulated for a few years, but it really, reached the wider world's attention with the discovery of Shor's algorithm 30 years ago. This was a fast method for factoring large numbers using a quantum computer, okay, finding prime factorizations. And, why does anyone care about that? Well, it so happens that most of the encryption that protects the internet, is based on the belief that factoring is hard, or that a few closely related problems are hard that Shor's algorithm can also solve, as it turns out. Okay, so what this showed everyone was that if someone managed to build a really scalable, fully programmable quantum computer, then the whole architecture of modern computer security and electronic commerce is all broken. Okay, so that's, at the very least, that's an application that interests some people. It's hard to put it forward as a positive application for the world. It sort of dramatically illustrates the reality of quantum speed-ups. And that's really what started quantum computing as a serious field. But now it's crucial to understand that to develop this algorithm, Shore really had to exploit very, very special properties of the factoring problem. Okay, and we don't know those same properties for, the traveling salesman problem, or for training a neural network, or for, most of the things that we want to do with our computers. So that there's a much, much larger range of problems where we only know how to get a more modest speed up from a quantum computer, right? And I think the scope of quantum speed up, how much can a quantum computer outperform a classical one, and for which tasks, is still very much an active research topic.
Yeah. So I want to segue into your AI work while we have a little bit of time here. You mentioned starting out with AI, and you've circled back in the last couple of years, and you're working at OpenAI, or where I'm sure you can't speak to specifics much, but I want to ask you, are you optimistic about AI being able to be safely used?
Well, in the short term, yes. The further you project out into the future, the harder it becomes to be confident. But, I feel like, given what we have seen in the last 5 years or so, that this revolution in generative AI, in deep learning, that we're now all seeing the fruits of, I think it is completely baked in that this is going to change ordinary life for all of us by, at least as much as, say, the personal computer and the internet did. The level of excitement right now, the only analogous thing that I've experienced was, the explosion of the internet and the web, in the early 90s, right? I was only an adolescent then. Okay. But we now effectively have computer software that you can talk to in English and that will understand you, and that, or at least will do what in a human would have been called understanding you.
Yeah.
And will give you a comprehending response. And, it is very far from perfect, as we all know. It is, it hallucinates, hems and haws, or it is too verbose. But, it is already good enough to be useful. I mean, millions of people are relying on ChatGPT and other tools to write code, to proofread things that they've written, to, suggest different ways to phrase, to do sort of clerical work, to do data analysis work. So this is already being used. And, once it gets more integrated with all of our other applications, then it seems inevitable at this point that the way that we will interact with our computers will just be the Star Trek way, right? It'll just be, you go and you say, computer, do this, and it does that thing. So that's been remarkable to witness. And I think, for computer scientists, most of the experts were pretty blindsided by this, right? They did not see this coming as quickly as it was. And the reason for that is that, they really expected, of course, these things would ultimately be possible, but it would require some really deep insights into the nature of intelligence itself, in order for us to reach this point. I think what almost no one expected was that it would be possible just by taking neural nets, back propagation, which are ideas that have been around for decades. I learned about them as an undergrad in the 90s, right? And just scaling them up by factors of millions, right? Using, gigantic computers, full of, GPUs running in data centers. And then equally important, gigantic amounts of training data, basically using the entire internet as a source of training data. And that you would just do that ridiculously simple-minded thing, and at some point it would start to work. So this is the really surprising part, and of course gives us an immediate direction to keep going, right? Build even bigger data centers, train on even more data. Okay, now it's not clear how long that can continue for. Eventually the amount of compute that's been used for AI has been growing by something like a factor of 10 every year. And if you just try to extrapolate that forward, you very quickly run into the total energy generation of the entire planet.
Yeah.
Which is why people have talked about, building more power plants, building nuclear plants, specifically for powering data centers, right? So there is a question. If we get a bottleneck, that's bad for AI progress, although maybe, and this was always the trade-off, maybe it's better for safety. If language models and image models and so forth only get incrementally better than they are now, then I think that making them safe is commensurate with making all kinds of previous technologies safe, whether that's the internet, whether that's cars, airplanes, and none of these things are perfectly safe. 40,000 people in the US die in car accidents every year. The internet has become, in many ways, a cesspool of misinformation and scams and things like that. Okay, but we learn to accept those things as byproducts of all of the good things that we get from these technologies, right? And, we learn to at least manage or cut down on the dangerous parts of technology, okay? And if AI kind of remains more or less like it is now, then I think that, yes, there will be many, many misuses of it. One that I've been thinking about especially is, millions of students are now using ChatGPT to cheat on their homework, right? Or to write their term papers. I've developed a way to watermark the outputs of large language models that should help, I think, in detect what came from a language model and what didn't. This is one example of how we can try to mitigate the misuse of AI. There are many other ideas, cryptographic backdoors. There are all kinds of tricks that we can play to try to make things safer. I mean, the most obvious example would be reinforcement learning, where basically you give it a little electric shock every time it says something that's either wildly inaccurate or racist or offensive or unhelpful or rude, right? And so, from many, many examples, it starts to learn what kinds of answers are humans looking for. I'm optimistic that we can sort of make current AI, tolerably safe.
Okay, last question. What does popular culture or general public get wrong about AI?
Oh, gosh. One of the most common things that I see is people will say, ChatGPT, for example, might appear to be intelligent, but let me explain it to you. Really, it is just a next token predictor. Really, it is just a function approximator. It's just a bunch of matrices and vectors. It is just math. And they will think that, okay, yeah, if people are impressed by it or scared by it or anything like that, like they must not understand that, right? And once you explain to them that it's really just math under the hood, then they'll see that this is completely deflationary, right? That there's nothing too interesting going on. And then the trouble is, if you want to be intellectually honest about it, then the next question you have to ask is, well, what are we? At some level, a brain is just a collection of neurons, right, that are firing, or not firing according to the laws of chemistry and physics, right? And yet somehow, you put together 100 billion of them, and it produces, all of the richness of the world as we perceive it. All of our experience somehow emerges from that. So I think it really does raise these questions that, that go, depending when you want to start the clock. Philosophers, worry, like Democritus worried about such things thousands of years ago. Okay. But Alan Turing in 1950 said, look, if you had a machine that you could not distinguish from a human by, any conversation or any empirical test, should you just regard it as conscious, as thinking in the same way that you would regard other people as conscious? So I think, like with any philosophy, people can believe what they want about that, but they should at least be aware of sort of the obvious counter arguments, right? Not just completely elide them. That's a mistake that people make in one direction, and of course you can find mistakes that people will make in the other direction, right? Where they will just unthinkingly rely on the outputs of GPT-4 or Claude 3 or whatever AIs they currently have access to. And, they'll just turn in a paper that it generates, not checking to see where the references, do the cited papers actually exist, or were they hallucinated? Does this argument make any sense, right? Like, is it happily supplying me with a proof for a false theorem, as it can sometimes do, as many undergraduates do also, right? So you have to be very aware of the limitations of the existing AIs. And I think that kind of comes naturally from just interacting with them enough.
Special thanks to Scott Aaronson. For the Discovery Files, I'm Nate Potker. Please subscribe wherever you get podcasts, and if you like our program, share with a friend and consider leaving a review. Discover how the U.S. National Science Foundation is advancing research at nsf.gov.